Okay, so today I'm happy to introduce Boedihardjo, who's an assistant professor at Michigan State University. Previously, March was a postdoc at ETH Zurich, UC Irvine, and UCLA. His work is about high-dimensional probability, functional analysis, and applications to differential privacy and Bose-Einstein distance. Thanks, March.
Thank you very much. Okay, so this is the outline of this presentation. There are two parts. One is on random matrix, the other is on random tensors. Okay, so for the random matrix, I'll first go through some literature on a special type of random matrix called Gaussian series random matrix. And in the second part of this talk, I will state the main results of this presentation. And in the next part of this talk, I'll give an application to theoretical computer science, the Matrix Spencer Conjecture. Okay, in the second part of this talk, I will study the problem of estimating the spectral norm of a random tensor with independent entries and state the main result. And after that, I will go through the prior literature on this problem. Okay, so Gaussian series random matrix is a random matrix of this form. It's a finite sum of GIAI. The GIs are random variables, but they're scalars, so they are independent standard normal random variables. The AIs are deterministic D by D matrices, so it's a linear combinations where the coefficients are random, but the matrices are deterministic. So that's a special type of random matrix that I'm going to study for the first part of this presentation. Examples of this were if you have a random matrix where all the entries are independent Gaussian, you can decompose that matrix entry by entry and write that into Gaussian series random matrix. Or more generally, if it is a sparse random matrix, most of the entries are zero, but it's only a very small minority of prescribed entries are independent Gaussians. You can also decompose that matrix entry by entry and write that into a Gaussian series random matrix, or if you have a Gaussian Toeplitz matrix, where it's a random Toeplitz matrix where each diagonals are the same, have the same entries Gaussian, but among different diagonals they're independent Gaussian. You can also decompose that into a Gaussian series random matrix. There are also other examples of this. Okay, so the problem that I'm going to study is we want to estimate the spectral norm of a given Gaussian series random matrix. If you're given a Gaussian series random matrix, all these AIs, we want to estimate the spectral norm, and let's say we just want to know how large the expectation of the spectral norm is. The spectral norm is just the largest singular value of the matrix. Okay.
So you can get high probability bounds?
Yeah, there is always some concentration on this, yes. And in particular, this 100th moment, let's say it's the pth moment, and then to take it to the power 1 over p, it's going to be bounded by some constant multiple of this that depends on p. All right, so there is a classical bound. This is like in around the 1980s, several decades ago. So there is a lower bound, which is this thing, sum of all these matrices square, and then take the norm square root. And this thing means this inequality holds up to a universal constant factor. The upper bound is the same thing up to a constant factor times a square of b. So this is if AI saw the deterministic matrices are symmetric. If it's not symmetric, you can do Hermitian dilation and make it into symmetric, and there's some version of this. So anyway, so there is upper bound and lower bound, and the upper bound or lower bound match up to a constant times square root log dimension d by d matrix. So that's the d. Okay, so sometimes this factor is not needed. Sometimes you need that. For example, if you have a matrix where all the entries are independent standard normal random variables, then you actually don't need this. This is something like 2, and this is like 1 if you scale it by root d. But if you have a diagonal random matrix where the diagonal entries are independent Gaussians, then the spectral norm is just the largest diagonal entry in absolute value, and that's of all the square log d, and in that case you really need the square log d. So in particular, the square log d is the sharp one. Okay, so for now let's focus on this specific example. So let's assume that all the entries of this random matrix are independent. So we only assume they're independent, but not necessarily IID. So they can have different variance across the entries. And in other words, because they're Gaussian, so it's just some coefficient Bij, which is different for different entries, times the Gij that are independent standard normal random variables. In that specific case, all the entries are independent. What this bound gives is this thing. The spectral norm of this random matrix is bounded below by, you can think of this is very computable. You can think of this as like you take any row of Z, the spectral norm is at least any row of Z, and then you take the Euclidean norm of that row. Or you take, because it's symmetrical, you take any column of Z and then take the Euclidean norm of that column. This is at least the norm of each row of Z, the spectral norm. And it's bounded by the same thing with the square log factor. Okay, so it's up and low bound match up to the square log factor. But the next question is, can we remove this square log factor? But as I've mentioned before, sometimes you can remove, sometimes you cannot. But can we do a back estimate of this where it tells us when it is removable? So there is a refinement of this result. And
just a question. So these bounds don't depend on the number of sum-ends in the series, like the number of GIs.
Okay, so because
surprising?
for this one, yeah, it does not depend. And if we are in d by d, you can always write that as 1 to d squared. So even if it is more than d squared, you can reduce that to d squared because there are only d squared dimensions there. And for this, yeah, the ij are between 1 and d. And d is the dimension size of the matrix. Okay, so there is a refinement of that result obtained a decade ago, and this is widely used in applications. I think there are 300 citations, this result. Okay, so you can remove the square log d factor, but put the log d on a second order term. But this second term is usually much smaller than that term because the max of Bij only measures the size of one single entry, whereas this one measures the size of a sum of d number of entries squared and then square root. So that this is a sum of d number of things, whereas this is just one single thing. So in general, unless the random matrix is very inhomogeneous, this is usually dominated by this. For example, if all the Bij are equal to 1, then this will give you square root d, where this gives you 1, and square log d is much less than root d. So this is usually dominated by that unless it's very, very sparse, very, very inhomogeneous. So it is a refinement of the one that non-commutative Kinchen inequality gives. So instead of putting square log d, it's putting square log d on a much smaller term in general. Okay, so let's do an example. Suppose all the Bij's are 0, 1. Let's say most of them are 0. a very small minority of entries ij have Bij equal to 1. So you have a sparse random matrix with prescribed entries being independent and a Gaussian. What this bound gives is that, okay, this is bounded above by constant times square root s, where s is the maximum sparsity among all the rows. That means the maximum number of non-zero entries, the number of entries that equal to 1 in a row, but the maximum one among all the rows. So that's the maximum sparsity. Root s, that's what this gives, plus square root of d times, well, Bij's are either 0 or 1, so that's 1 here. So that's an upper bound, whereas if you apply this, you will get a lower bound of root s, but it's also true that root square root of d is a lower bound, as long as you assume that there's no row where the entire row is 0. If the entire row is 0, you can just remove that row because that's a degeneracy. So assume there's no degeneracy, then the random matrix will have at least d number of entries that are independent than a Gaussian, and because of that, square root of d is also a lower bound. So square root of d plus root s is an upper bound up to a constant factor, and it's also a lower bound up to a constant factor. So that's matching upper and lower bounds. So this gives a sharp estimate for the spectral norm up to a constant. Whereas if you apply the non-commutative Kinchian inequality, this thing here, if you apply this one, or in the case of independent entry case, you have square root of d times this thing will be root s, and then you have square root of d times root s, whereas this gives plus, which is not only sharper than that, but it's actually the exactly equal to that up to universal constant factor. Okay, next question is, this is only for the independent entry model. Can we generalize this to Gaussian series random matrix in general? So let's go back to this. So that's the non-commutative Kinchian. In the special case where it's independent entry model, this is what the non-commutative Kinchian gives, and that's the special case. But going back to the non-commutative Kinchian, can we get a refinement of this? So Bandeira and Handel a decade ago were able to get a refinement of this result, but can we get that refinement in the most general case? That's the problem. So so this is a refinement of the non-commutative Kinchian inequality in the case where entries are independent. Can we do this type of refinements in the most general case for general Gaussian series random matrix? Can we refine the non-commutative Kinchian inequality, not just for the independent entry model, but in the general setting? Okay, so just want to mention it again. Sometimes the square root of d is not needed. Sometimes it's needed, like if you have a diagonal random matrix, all the entries are diagonal, then ID, all the entries on the diagonal ID is in a Gaussian, then you really need a square root of d. The largest one will be of order square root of d. So you need that sometimes. So the question is, can we do the refinements by Bandeira and Handel, but not just for the independent entry model case, but in the most general setting? Can we do that kind of result? So for the independent entry case, yes, that's what they obtained, but in the most general setting, can we, instead of putting square root of d on the first term, we have a second term, and then put the square root of d on the second term instead of on the first term. Okay. All right. And this is the first main result of this presentation. Suppose you have a Gaussian series random matrix, so the non-commutative Kinchian inequality gives you this thing times square root of d. Now instead of putting square log d on the main term, we have now, I think the correct thing should be square log d, but we can only get log d to the power 3/2, and that's the second term that we get. So what is this thing? Vec of AI is, so all the AIs are, A1 to AN are d by d matrix. We treat the matrix as a vector. By treating matrix as a vector, we get a vector that has d squared number of entries. So once you treat the matrix as a vector, you take the outer product of that vector with itself, and then take the sum, and then take the spectral norm. So this is also a computable quantity. And in the case where the entries are independent, what this gives is it kind of recovers the results by Bandeira and Handel, except that the one that they got in the independent entry case, they get the optimal square log d, but we can only do log d to the power 3/2. And in fact, what I didn't mention is they get a good constant factor, when that's epsilon. Well, actually, we also get a good constant factor, but it's in another version of this, we actually get the optimal constant of 2. But okay, let's not talk about the exact constant factor. We actually get the optimal constant 2 in another version of this. But the main deficiency is the square log d becomes log d power 3/2. But that's okay because it's in the second term, and as I mentioned before, the second term in general, in most of the cases, is dominated by the first term. So as long as it is dominated, it's only this term counts, so it's okay if it is square log d becomes log d power 3/2 because it's on the second term. Okay, so that's the main result of this presentation for random matrices. Yes?
Yeah, so just wondering, does the result also hold for step function or only for step functionality?
Yeah, if you replace Gaussian by sub-Gaussian, it is also, let me see, it's also true. Gaussian by sub-Gaussian. If you replace by Rademacher, then it's true. But sub-Gaussian, okay, for this one, if you replace by sub-Gaussian, then yes. For this one, it's going to be yes for sub-Gaussian, but that one I haven't really thought about. For Rademacher, it's true, because if we apply symmetrization, we get this thing. So in particular, if you do it for Rademacher, yes, but Gaussian, I still have to think about this. Yeah, I have to think about Gaussian. Okay, if you apply symmetrization, that's what you get, and you can apply the results to, as I said, very sparse matrices. Pattern matrices are kind of like Toeplitz matrix, like a lot of prescribed entries are forced to be the same, but other than that, they are independent. So it's kind of like random Toeplitz matrix. Block models, which is, instead of independence entries, is independence block. And I think what we get is, let's say we're...
Sorry, so this result here though would apply to sub-Gaussian GI?
It does not, let me see,
Just assuming.
let me see, sub-Gaussian, if you put sub-Gaussian, let me see.
Set ZI to be GI AI?
Yeah, I think so. If it is sub-Gaussian, no. You have to deal with this max thing there. If you put GIAI, I think you would get, I think, Frobenius norm square, and then okay, so the covariance thing, is equal to this thing, and if in the sub-Gaussian case, that's also okay. But in the sub-Gaussian case, you have the Frobenius norm of AI squared times that sub-Gaussian squared, and the max of that, and so you have to deal with that thing. If it's Rademacher, it's okay because Rademacher squared is 1 for sub-Gaussian. So Gaussian is good, but then we might have log d to the power 3, something like that in this term. Okay, in the block model, I think let's say you have a d by d block matrix, so d blocks and d blocks, and let's say each block is d over polylog of d by d polylog of d. I think in that case we get a sharp estimate for the spectral norm, if I remember correctly. All right. Okay, so going back to sub-Gaussian, I think maybe this is true for sub-Gaussian, but I think what I can guarantee is true is replace log d to the power 3 over 2 by maybe some other exponent, maybe 5 or 7 over 2. Yes.
So in this theorem, GI is still independent.
The ZIs are independent. So
in previous line.
there's no Z here. Oh, this one?
No, in the theorem, Z1 to Zn are independent.
G1. Yeah, G1 to Gn are independent standard normal random variables.
I thought you said you want to remove the independent. No.
Okay, so instead of independent entries, we want independent blocks. That's what I said.
What do you mean by independent block?
Let's write this. Okay, so it's a block matrix where inside the block the entries might not be independent, but this block and that block, they're completely independent. Each block is random. All the blocks are random. Okay. All right. So let's do an application of this result. I think this comes from the theoretical computer science. Suppose you have n number of matrices, and each of them is n by n. It's the same n. There's another version where n number of matrices, where each of them is d by d, but the most interesting case of this conjecture is n number of matrices, each of them n by n with the same n. Okay, each of them has spectral norm at most 1, and can we find, so there's nothing random here, no randomness here. Can we find plus minus 1 entry so that this sum has norm at most constant times root n? And you can think of this sequence of plus minus 1 coefficients as like a partition of 1 to n, and then S represents those index where epsilon I is equal to 1, and S complements are those I for which epsilon I is minus 1. And then this becomes this, and this will be kind of measuring, is there a way of partitioning this A1 to AN such that it's kind of balanced? Balanced in the sense that you sum over AI on this block of the partition and on the complements block of the partition. If you sum them up, they are close up to this area. So how balanced can we partition A1 to AN? Okay, and this conjecture is saying that the balanced error is bounded by a constant times square root, and it's kind of like the discrepancy notion. Okay, so First of all, it's impossible to do better than square root n, because even in the case where each AI is the following, AI is the matrix where it has entry 1 on the first row ith column, and all the other entries are 0. So just entry 1 on one of the entry, first row ith column, the others are all 0. Even in that case, if you look at this sum, what is this going to give? You will get a matrix where only the first row is non-zero, but for the first row, what you have is epsilon 1, epsilon 2, all the way to epsilon n. And if you take the Euclidean norm of that row, you already get root n. So even in such a very sparse case, you can't do better than root n. Now in the general case, if we only assume that the norm is at most 1, and if you just blindly, randomly choose epsilon to epsilon n, independently, uniformly from -1 and 1, the non-commutative Kinchian inequality already gives you this, and this thing is bounded by root n. So in the most general case, just blindly choosing -1 and 1 completely independently and randomly, you actually get square root n times log n, but you can't do better than root n even in such a trivial case. Okay, so the question is, in the most general case, can we do root n instead of n log n? And this turns out to be notoriously difficult conjecture. Okay, so this was obtained 3 years ago and published 2 years ago. If we impose an additional assumption that the rank, the rank is at most n over log n cubed, because if you don't put any assumption, just this one, automatically the rank is at most n, because the n by n, so the rank is always at most n, but you put the assumption that it's at most n over log n cubed, then you can do that. We don't even have the square log n, it's really root n. Okay. And this is a consequence of the first result that I showed you, the Gaussian series random matrix that we obtained. The year before they obtained this, so the one on Gaussian series is essential ingredients in the proof of this result as stated in the abstract. The year before, the best result that was obtained requires assuming the rank at most root n, and it's completely different proof. Okay, so how do they actually use our result to prove this? Okay, so let's say if you just blindly choose the epsilon 1 to epsilon randomly, independent, what our result gives is this. Now, of course, our result is Gaussian, but if you can prove it for Gaussian, you can prove it for random upper, plus -1 independent. But for Gaussian, that's what we obtain in our result. Now, if this is less than equal, if this is dominated by this, then yes, because this itself is bounded by root n times a constant, then yes. But this thing is not always dominated by this thing, so we have to make some changes to make it so that we can get rid of this term. Now, but of course, as I said, here we just blindly choose the Gaussian completely independence randomly. But we can do a smarter way of choosing the Gaussian. Now, of course, eventually we want plus and -1, but if we can do it at the Gaussian level, there's some way they are able to turn that to plus -1. Okay, so this is independent Gaussian, but there's a smarter way of choosing those Gaussian, because we don't have to prove it for random epsilon I, we just have to show one set of choice epsilon to epsilon n. So we can choose it in a smarter way. Okay, the smarter way to choose the G1 to Gn, instead of having them to be independent Gaussian, choose them from a subspace of our n. So Rn has dimension n, and it's subspace 1 minus g delta times n dimension. And what is that subspace? It's kind of like from a PCA. There's some kind of matrix, but then you just take the best 1 minus delta times n eigenvectors, so that what you get is the following. So if you choose G1 to Gn completely independent, Gaussian, then you get the spectral norm. But what's the spectral norm? Spectral norm is the largest eigenvalue of this positive semi-definite matrix. So if you choose it from a subspace, instead of the largest eigenvalue of this, what you get is the delta nth largest eigenvalue. But the delta nth largest eigenvalue is bounded by the trace of that, and the trace is just the sum of all the eigenvalues divided by delta n. And the delta nth largest eigenvalue is, you can bound it by this. So we have this one, if you choose the G1 to Gn in a smarter way. And the trace of this is a rank 1 matrix. The trace of a rank 1 matrix is just the norm of this square. So what's the norm of this? This is a matrix treated as a vector. You take a norm, and that's just the Frobenius norm. And if we assume the rank of AI is bounded by n over log n cubed, then you can bound the Frobenius norm by this thing. And then once you have log n cubed on the denominator, it will cancel with this thing, and eventually the whole thing will be bounded by constant times root n. So that's how they apply our result. Now, of course, this is on the Gaussian level, then there's still one more step to turn from Gaussian to a plus minus 1 entries, and that's not in this, that's not here. Okay, so that's what they get. The rank is really just to make the Frobenius norm bounded by something so that you have log n cubed on the denominator, and then you get this result using our result. Okay, so there are other, so this is just one consequence of our results. There are other consequences of our results on the Gaussian series random matrix, like sparse subspace embedding, I saw. And there's also an application to federated learning, if I remember correctly. All right.
So the proof is somewhat constructed, is it, for finding the epsilons?
Yes, they also show that there is an algorithm to construct the epsilon to epsilon n in polynomial time. Yes. Okay. But I have to say the constant is really large. The delta is something like 1 over 6,000, something like that. So practically, probably not so good, because non-commutative Keynesian inequality already gives you the log n with a clean constant. And if you do this type of thing, you might have to take delta to be 1 over 6,000, something like that. Okay, so now let's go to the second part of this presentation, random tensors. Okay, so let me first do the setup. The tensor space is the tensor product of R copies of the Euclidean space Rd. So it consists of linear combinations of this x1 tensor to xr. And there's also a canonical inner product on this vector space, which is this thing. Okay, the spectral norm of tensor is an extension of the notion of spectral norm for matrices. And that's supremum of Z with this thing, where we take supremum over x1 to xr in the Euclidean unit form. So if R equal to 2, the tensor space is the space of matrices, and this gives you the spectral norm, the largest singular value. All right, so now the question is, can we get a good estimate for the spectral norm of a given random tensor with independent entries. All the z's, z of I1 to IR are independent. Okay, so as I said, they can be they're independent but not necessarily ID, so it can be very sparse. So could be that most of the entries are 0, only a very small minority of the entries are ID rather more, let's say, but most of them are 0. Can we still get a good estimate for the spectral norm? Okay, so there are some lower bounds that are kind of obvious. For example, so let's first do R equal 2. We actually did something like that, but just recall it quickly. There's a lower bound where the spectral norm is bounded below by the Euclidean norm of each row of z. If you take the I1th row of z and take the Euclidean norm, that's what you get. And it's true for every row I1, so it's true for max of I1. And the Euclidean norm, the spectral norm is at least the Euclidean norm of every column of z. So the I2 column of z is this, and it's true for every column I2, so max over I2. Okay, and there's also another bound, which is spectral norm is at least the max of every entry of z. And upper bound, so the one I showed you before is for Gaussian, and if you use symmetrization, you will get this thing. Suppose there's a number L that uniformly and almost surely bounds all the entries of z, then, well, first of all, you have these two on the lower bound, so you need that in the upper bound. You just have that number L times square log d. And because L represents the size of just one entry of z, where this represents the size of the sum of the number of entries of z squared and then square root, this is usually dominated by this thing. This is just one entry, this is the number of entries. And if it's dominated by that, you can neglect this and you get a sharp matching upper and lower bounds if this is dominated by that. So that's in the R equal 2. We've seen that before. We've seen that before for Gaussian, but this is for independence, just doing symmetrization. Okay, now let's go back to the tensor case. Can we do that kind of result, this result, but for tensor? So this matrix, can we do it for tensor? That's the question. So we can also do a kind of lower bound, because by the definition of spectral norm, the spectral norm is suprema of z with arbitrary x1 to xr in the ball. And we can take x1 to xr to be these things where E1, all the EJs form the canonical basis for RD, and the J1 to JR are arbitrary indexes between 1 and D, except for the case when we still keep the vector x. And the inner product will reduce to this sum, and the inner product of x comma, you can pull that out from the sum, and then supremum of inner product x comma this thing over x in the ball, you can write that as the Euclidean norm of this vector. And then Euclidean norm by definition is square roots of the sum of these things square. Okay, so that's a lower bound. So what about upper bound? Before I go to upper bound, so this is true for every arbitrary indexes J1 to JR, so we can take expectation on both sides, and it's true for all J1 to JR. So you can take max over all these indexes, and K from 1 to R is the choice of the position K. So when R equal to 2, for example, you have K between 1 and 2, and K equal to 1 gives you the rows, K equal to 2 gives you the columns. And we have something like that for matrices. And so this is a generalization of what we did for matrices in the context of tensors. Okay, upper bound. Before I go to upper bound, there's one more lower bound. Is the spectral norm is bounded by every entry of Z in absolute value. The upper bound is the same thing as the lower bound, except we have to add L, a number that bounds all the entries of Z uniformly and almost surely, times log D square. And just like for matrices, because L represents the size of one entry of Z in absolute value, whereas this represents the sum of the number of entries of Z. So oftentimes this is dominated by that one, and in that case we have matching upper and lower bounds. The constant only depends on R. I think in the case where we have everything homogeneous, it's like square root R log R, but I can only get R square, something R square for the constant. Okay, so that's the main results for the second part of this talk on tensors.
There's only like 5 or so minutes.
Okay. All right. So compared to the result by Bandeira and Handel, they get the optimal square log D dependence on the dimension, but I can only get log D square. But this is on the second term, so as long as this is dominated by the first term, we have matching upper and lower bounds. Okay, so now let's go to the prior literature. First of all, the reason why bounding the spectral norm for tensors is more difficult than for matrices is because for matrices, one of the most common techniques for bounding the spectral norm is the moments method. The spectral norm is bounded below by the normalized trace, the trace over the dimension of x to the power 2p, the whole thing to the power 1 over 2p, and bounded above by the same thing, times d power 1 over 2p. So if you take the moments p to be of order log d, then this will be of order 1, and then this and this have the same magnitude. And if you take the p to be a big constant times log d, then this will be close to 1, and that gives you an approximation for the spectral norm. In the context of tensors, the reason why we can't do this moments method for tensors is that if you could really do it for tensors, unlike the spectral norm of matrix, spectral norm of matrix is computable in polynomial time. For tensor is NP hard. So if there's any reasonable way of extending the moments method to tensors, then you can do this in polynomial time. And if there's any reasonable extension of this to tensor, if that can be done in polynomial time, but on the other side it's not computable in polynomial time, and that's an obstruction to extending this moments method to tensors. And I mentioned this is because, in particular, the results by Bandeira and Handel uses the moments method. So we have to come up with a completely different proof. Okay, but there's still some results that avoids using moments method. Injective norm is just spectral norm. So this one, this is actually the first result on bounding the spectral norm of the random tensor. So it just uses flat root D times the L that uniformly bounds all the entries. So this will be sharp if all the entries are of order 1. But then in the case like what these people did, when they applied to tensor sparsification, use a sparse tensor to approximate a given tensor, they have to bound the spectral norm of a sparse random tensor. But in that case, if you have a sparse random tensor, because this upper bound is not very friendly when it is sparse, it does not take into account the sparsity. Like, if you really want to take into account the sparsity, you have to have this thing involved in the upper bound, but it's not. It only depends on the uniform number L that bounds all the entry times the flat root D. But whereas if it's sparse, instead of root D would be something that depends on the sparsity. But no, it just have a flat root D on the bound. So even though it's not good, it doesn't take into account the sparsity of Z, but at least they find it very satisfactory. And this is still much better than the Frobenius norm of Z, even though it's not sharp. Okay, another approach, this is actually a decade before the result by Bandeira and Handel. the town actually do the same thing but with this thing. So this thing is good in the sense that there's no dimension factor, but in the case when it is sparse, it's better than the flat root D, but it's still not sharp. The good thing is it doesn't use the moments method, so the proof can potentially be extended to tensors, because there's no moments method used in the proof, and indeed 3 months ago it got extended to tensors. But because even in the case for random matrix, it's not sharp for matrix, so it's also not sharp for tensors. And okay, another attempt that was done for estimating the spectral norm of a random tensor was in the context of Boedihardjo hypergraph. So you have all the entries being independent, but they are Bernoulli. So with probability, this thing is equal to 1 minus that thing is 0. Using some combinatorial argument that was half a decade ago, they obtained this thing where P max is the max of all these probabilities. Whereas if you use the result that I proved, you'll get this thing. And if you compare this with that, each of these P, I1 to IR are bounded by P max. And this is obviously bounded by square roots P max times D. And in fact, this whole term here is also a lower bound for that thing. So this is only upper bound, but this thing is also a lower bound for that thing. So as long as the log D square is dominated by this thing, then we get matching upper and lower bounds for that thing. So the difference is that this is a multiplicative factor by polylog D. This is the additive factor of polylog D. Okay, and that's the end of this presentation.
Questions?
In the result you showed in this last slide, where you had the multiplicative polylog D factor, how does this come up in the proof?
So they use this consumerity arguments, which I don't really know. So in the case of R equal to 2 for matrices, just graphs, that technique is really good, but I haven't really read the proof, but in the context of hypergraphs when R bigger than 2, then that argument has some deficiency.
Are your proof techniques useful for other norms besides spectral norm?
What are the other norms?
Maybe nuclear norm, which is the dual norm of the spectrum?
No, the proof uses this a modified version of Snap-Invernic. So because a spectral norm we can write this spectral norm as a supremum of a Gaussian process, and then use a version of Snap-Invernic to bound the supremum of Gaussian process. The nuclear norm, I don't think you can write that as supremum of the Gaussian process. Yes.
Earlier you mentioned that there's some version, I forget of which result, but where you have a block model where there's no dependence between the blocks. I was wondering if there are versions of that statement where there's some weak dependence between blocks. Maybe you can bound, I don't know, the covariances of entries across blocks or something.
Yeah, so these are just examples. So even if the blocks, so any matrix where the entries are jointly Gaussian, so it doesn't have to be independent Gaussian, just jointly Gaussian, result is applicable. So yes, even if the blocks are correlated, you can use that result, yes.
Yeah, I guess what I have in mind is like matrix completion type settings. So there, you might have missing entries, and then the pattern of missingness has some correlation, but it's not a jointly Gaussian distribution.
If it is not jointly Gaussian, then no, you cannot apply. It has to be jointly Gaussian. You can have arbitrary correlation, but it has to be jointly Gaussian. If they are not jointly Gaussian, you cannot write that matrix as a Gaussian series random matrix. If they're jointly Gaussian, even if the correlations are arbitrary, you can write that as a Gaussian series random matrix.
So what do you think is the next open problem to tackle in this direction?
Wow. I think it's just reducing the 3/2 to the square log b. But we just don't bother to try that. Maybe it takes 100 more pages to prove that.
But what about the tensor part I thought?
Oh, the tensor part. Okay, the tensor part, there are problems remaining. And I want to turn on the lights and have a marker so that I can write something on the board. I don't need this thing.
Don't have a marker.
No marker. How can I write? Okay, it's the following. I can say it even if I can write it. Okay, the problem is the following. So here the entries are independent, but you can also do the Gaussian series random tensor, sum of GIAI, where the AIs are tensors. And then can we show that non-commutative Kinchen inequality holds for tensors? So suppose that instead of AI being deterministic matrices, they're deterministic symmetric tensors. Let's say, can we bound this above by, let's say, polylog of d, not even root square log d. Polylog of d times, okay, let's put the norm inside. The sum of the norm of AI square, where we have spectral norm of AI. That is a very difficult question in the field.